I'm the chemistry guy, and in this video we are going to talk about what stuff is made of. In particular, from the hardest metal to the air around us, everything is made of atoms. We will learn about the elements and the fact that each element can have different isotopes. Okay, let's get started. Everything around us, whether it's the hardest rock or the air, is composed of atoms. Okay, though the picture shown below is very inaccurate, and we'll get into that later, the center of every atom is a nucleus, and it is positively charged. It is surrounded by electrons, and they are negatively charged. Most nuclei contain protons, which have a charge of +1, and neutrons, which have no charge. Protons and neutrons are more than 1,800 times heavier than the electron, so virtually all of the mass of the atom is in the nucleus. Electrons are very small, move very fast, and have a charge of -1. A neutral atom, meaning it has no charge, has as many negative electrons traveling around the nucleus as there are positive protons in the nucleus. If there are more protons in the nucleus than electrons orbiting around it, then there are more positive charges than there are negative charges, and the atom will have a net positive charge. It is called a cation. If there are more electrons around the nucleus than protons in the nucleus, then there are more negative charges in the atom than there are positive, and the atom has a net negative charge. It is called an anion. Cations and anions are collectively just known as ions. Different atoms have different number of protons in the nucleus, and therefore a different number of electrons traveling around the nucleus if the atom has no net charge. These different atoms are known as the elements and are arranged in the periodic table of the elements. The simplest element is hydrogen. It contains a single proton in the nucleus and a single electron traveling around it. It is also possible to have a neutron in the nucleus. This is called deuterium, as opposed to hydrogen, and it is an isotope of hydrogen. Isotopes of any given element therefore have the same number of protons in the nucleus, but different numbers of neutrons. Here we have a slightly closer look at the periodic table, and we will look closely at one element, carbon. The atomic number for carbon is 6, which means that there are 6 protons in the nucleus. The elemental symbol for carbon is just the capital letter C, and the atomic mass of carbon is 12.011. The atomic mass of an element is the weighted average of the weights of all isotopes of that element. That may seem confusing, but we will clarify this soon. As an example, we will look at carbon. It contains 2 stable isotopes as shown in the following table. Carbon-12, which is the first one, has a mass of exactly 12, and it accounts for 98.93% of all carbon atoms. The 12 in carbon-12 is the mass number, which is just the sum of the number of protons and neutrons in the nucleus. Since carbon has 6 protons, its atomic number is 6, then carbon-12 must have 6 neutrons in the nucleus. Conversely, carbon-13 accounts for the remaining 1.07% of all carbon atoms. Since it must contain 6 protons in order to be carbon, there must be 7 neutrons in the nucleus to give it a mass number of 13. The following procedure is used to determine the overall atomic mass of carbon. Since 98.93% of all carbon atoms are carbon-12 with a weight of 12, and 1.07% of the carbons are carbon-13 with a weight of 13.003, etc., then we use the following expression. Okay, we've got 9.9893, which is 98.93%, times 12, the exact weight of carbon-12, plus 0.0107 or 1.07% times the exact atomic weight of carbon-13, and when we calculate this out, we end up with a value of 12.0107, which is rounded to 12.011 in the periodic table. We can work this problem backwards for any element that contains two stable isotopes. For example, lithium has an atomic number of 3, which means that there are 3 protons in the nucleus. Lithium-6 therefore has 3 protons and 3 neutrons in the nucleus to give it a mass number of 6, and it has an elemental mass of 6.015. Lithium-7 therefore must have 3 protons and 4 neutrons in the nucleus to give it a mass number of 7, and it has an elemental mass of 7.016. If the atomic mass of lithium is 6.94, what is the percentage of lithium that is lithium-6? In order to solve this, we will let X be the fraction of lithium that is lithium-6, and Y be the fraction that is lithium-7. Then the atomic mass is determined from the following equation. 6.94, which is the atomic mass, is equal to X, that fraction times 6.015, plus the fraction that is lithium-7 times 7.016. We also know that X plus Y must be equal to 1 because they are the only 2 stable isotopes of lithium. So what is not lithium-6 has to be lithium-7. This can be rewritten as Y is equal to 1.0 minus X and inserted into this top equation to give 6.94 is equal to X times 6.015 plus 1 minus X times 7.016. This is the equation that we came up with in the last slide, where X is the fraction of lithium that's lithium-6. We can expand this last term to be 7.016 minus X times 7.016, and then we can collect the X terms, which gives us that 6.94 is equal to 7.016 plus X times 6.015 minus 7.016. Okay, I collected these two terms together. Or 6.94 is equal to 7.016 minus X times 1.000882, which is the difference of these is negative 1.00 whatever, and so I move the minus sign out in front. Moving the term in X to the right and 6.94 to the left gives us, I moved this to this equation, so this side, so it became positive, is equal to 7.016 minus 6.94, or 0.076004. So we now have that the fraction of lithiums that's lithium-6 times 1.000882 is equal to 0.076004. If we divide both sides of this equation by that number, we get that X is equal to 7.06004 divided by 1.000882, or X is equal to 0.075937. Since the atomic mass of lithium is given as 6.94, this has only 3 significant digits. So we say that X, the fraction that is lithium-6, is 0.0759. Notice that this leading 0 is not a significant digit, only these are. In other words, 7.95% of all lithiums is lithium-6, and the remaining 92.41% of lithiums must be lithium-7. A lot of information was presented in just these few slides, so we'll review it one more time. And all atoms contain a nucleus that is composed of protons and neutrons and is surrounded by electrons. The proton has a +1 charge, the neutron is neutral, and the electron has a -1 charge. If the number of electrons surrounding the nucleus is not equal to the number of protons in the nucleus, the atom will have a net charge and is called an ion. If the net charge is positive, which means fewer electrons than protons, it is called a cation, while if the net charge is negative, which is more electrons around the nucleus than protons in the nucleus, it is an anion. The elements are atoms with different numbers of protons in the nucleus. Any given element may exist in different forms, known as isotopes, that have different numbers of neutrons in the nucleus. The atomic number is different for each element, and it denotes the number of protons in the nucleus. The atomic symbol is a 1 or 2 letter code denoting the element, so instead of writing the element with atomic number of 6, we can write carbon or just capital C. Each isotope has a given mass based on a scale that defines carbon-12 as having a mass of exactly 12.0. We will discuss the units later. The atomic mass of an element is the fractional abundance of an isotope times the mass of that isotope, summed over all naturally occurring isotopes of that element. In common lingo, this is known as the atomic weight, but weight only has a meaning when standing on Earth. In deep space, objects are weightless, but their mass is the same, unless they're traveling close to the speed of light, but that we're not going to get into. The mass number is the sum of the number of protons and neutrons in the nucleus, so carbon-12 has a mass number of 12 and contains 6 protons, since it's carbon, and 6 neutrons in the nucleus. Given the mass or weights of the stable isotopes of an element and their natural abundance, we can calculate the atomic mass or atomic weight of that element. Also, if there are only 2 stable isotopes, we can calculate their abundance if we know the weights of the isotopes and the overall atomic weight. I hope you enjoyed this video, and if you enjoyed it, I hope you will support my Patreon page.